In this video, I'm going to go through AQA AS Chemistry paper. This is June 2016, paper 2, and this is the second half of this paper. I covered the first half in an earlier video. Okay. Right, we've got an alkene, 3-methyl-pentane reacts with hydrogen to form a mixture. Right, draw the structure of Z3-methyl-pentane. Okay, so let's just draw out so it's pent, 5 carbons, 3-methyl, so I'm going to put the methyl on there, pentane, so it's between carbons 2 and 3, so that would be the structure. Okay, now I'm going to draw it out so you can see the EZ configuration. So draw the double bond here. Now look what we've got attached to this carbon, the red carbon. We've got an ethyl group and a methyl group. Now it's going to be the ethyl which is the highest priority. On this carbon here, we've got a methyl group and we've got a hydrogen, and it's going to be the methyl which is the high priority. So we need to have here we need to have the methyl up here and hydrogen there. On this carbon we need to have an ethyl group up here, so CH2 CH3, and we want the CH3 there, and that is the Z isomer together. So the two high priority groups, that one and that one, are on the same side of the molecule. Name and outline a reaction mechanism for the formation of 3-bromo-3-methyl-pentane from the reaction of the alkane with hydrogen bromide. Okay, so this is a big question. Now the name of the mechanism, of course, any alkene reacting with HBr, that is electrophilic addition. Okay, this is a lot of marks going for this question because there are two possible products. There is the major product, 3-bromo, 3-methyl-pentane, and the minor product. Okay, and we've got to explain why we get that. So let's go through the mechanism then. So we've got 3-methyl-pentane. Let's draw that. So we're going to have, drew it before. We have that there, and on this side we've got a methyl group, and we have an ethyl group, which I'll just draw as C2H5. Okay. Now the hydrogen bromide is going to come along. We have a delta positive on that hydrogen there. And so a pair of electrons is going to jump from the pi bond onto the hydrogen, and then this bond between the hydrogen and the bromine is going to break. Both electrons go to the bromine. So if we draw the product there, we're going to have a C2H5. So this is the intermediate, sorry. We're going to have a methyl group here. Now we can have the hydrogen sticking onto either, we can either draw it so the hydrogen goes to this red carbon or going to the green carbon. Now to give us the major product, the hydrogen goes to that one there, and that means this is a carbocation. So that is, what kind of a carbocation is that? It is a tertiary carbocation. Now we're going to mention later on at the end here, we're going to say that if it had stuck to the other carbon, I'll draw it in a different color. If the hydrogen had stuck onto this carbon instead, we wouldn't end up with a tertiary, we would end up with a secondary carbocation. Okay, this is a secondary carbocation because the positive charge is on a carbon which is attached to just 2 other carbons, not 3, as is the case with this one here. Right, so we'll keep that structure there for later, but let's do the next step in the mechanism. Now we've got Br minus formed also. There's actually 4 lone pairs there. We just draw one of them, and that lone pair is going to go there to form a bond to that carbon, the carbocation carbon. And we are going to get the final product, which is 3-methyl 3-bromo, 3-bromo 3-methyl, sorry. Pentane. Okay. Now, so that will get you about 4 marks, and so for the last 3 marks, I think, or maybe last 2 marks, you need to say that why do we get more of this? This is the why do we get more of the major product, and that's because it becomes through the tertiary carbocation, which is more stable than this is a secondary carbocation, less stable. Why is the tertiary carbocation more stable? Well, it is because you have got 3 alkyl groups, okay, that one, and that one. Sorry, draw it on the carbocation, sorry. You've got 3 alkyl groups, and they all have a slight tendency to push charge away from themselves into the carbocation, or release negative charge to the positive carbon atom. That reduces the intensity of the positive charge, and it makes it more stable. So that will get you your 7 marks. It's a long question. Okay. The sort of classic mistake there is to say that the products are more stable. The people will say this product is more stable than that product. Well, it's not. It's not the product. It's the intermediate carbocations that they're formed from that have a difference in stability. Okay. Right. So rate of reaction question now. Okay. So we have got ethanoic acid react with magnesium. It's going to make, so there's the, well, that equation is a bit small. Okay. Okay. Right. So we've got the reaction there. So we've got 2 ethanoic acids reacting with 1 magnesium. With the aid of calculation, show the magnesium is in excess. Right. What we're going to do there then? Okay. So we're going to say, right, moles of magnesium is equal to mass over mR. AR for magnesium because it's an atom. The mass is, right, we've got 396 milligrams, so that's 0.396 grams divided by 1,000. 0.396 divided by 24.3, and that is going to give us 0.01629 moles of magnesium. Let's do the moles of ethanoic acid now. Now that's going to be concentration times the volume. The concentration is 0.6, the volume is 30 over 1,000. Which gives us 0.18. Now we need 2 times the moles of ethanoic acid for magnesium. So we need, if it was to have enough ethanoic acid, we need 2 times that. 2 times 0.1629, which is equal to 0.326, 0.0326 moles, and we haven't got anywhere near enough. That we've only got about half of that amount. So the magnesium is in excess. Yeah. Okay, right. I'll paste that in there unless we've done that question already. Right, now the reaction was repeated using 20 centimeters cubed this time. Okay, a different amount of ethanoic acid. Now, how many moles of ethanoic acid do we have to start in the first, for the first time? We worked it out, we had 0.018. So this one here, that's with 0.018 moles ethanoic. And the concentration of that, by the way, was, what did it say it was? It was 0.6 mole per decimeter cubed. Right, in this new one here, we're using a higher concentration of ethanoic acid. Okay, so it will go faster because it's a higher concentration, but we've got to see how many moles we've got. So let's do here in this new one, the moles of ethanoic is equal to conc times volume, 0.8 times 0.02, that's 20 over 1,000, gives us 0.016. Okay, so we've got less moles of that. Now, because the ethanoic acid is a limiting reagent, right? So we get that much hydrogen produced with 0.18. How much are we going to get with 0.16? Well, it's going to be 0.18. No, it's going to be 0.18. 0.16 over 0.18. What's that? 16 divided by 18. So we're only going to get right. So if we're going to get less. Okay, now let's just see what we're going to get. Right. So if you got, I'll just do it a slightly different way. So where should it stop? Right. That's with 0.018. So that would be with 0.016, 14, and so on all the way down to 0 there. So our line needs to level out here. Okay. But the rate of reaction is faster, so it's going to level out faster. So it's going to be something like that. There's 2 marks going for that question. Okay, one is for the rate showing, so that's steeper there, and the second mark is for leveling it out in the right place. And you're not going to get as much hydrogen produced because you've got less moles of ethanoic acid. You've got what is it? 0.16 over 0.18 is that's equal to 8/9, isn't it? Yeah. You're only going to 8/9 as much as that. That's 9 of those little squares. So you stop on the 8th one there. It's another way of looking at it. Okay, so that's that question there. Right, now onto the multiple choice section. Which of the following compounds would form a red with failings? Okay, so it's aldehydes, and of course this is the way you write an aldehyde on one line, CHO. So it's that. That's the only one. This one is a ketone, so that won't work. That's a carboxylic acid, and that's a nitrile. So it's B. Fairly straightforward question. Pentane nitrile can be made from 1-bromobutane with potassium cyanide. Okay, so let's just draw how that would be made. So you're going to have so 1-bromobutane is that, and you're going to turn it into that. So what's happened there? How's that work? How's that working? We've got a delta positive on that carbon, and so you're going to get a cyanide ion is going to come along, and it's going to go there like that. And so this is a nucleophile, and you're swapping it for the bromine, so it's nucleophilic substitution is the right answer. Okay, so propene is made by the dehydration of propan-2-ol. What's the percentage yield when 30 grams? Okay, so let's just write down the equation for that. We're going to get propanol, which which is C3H8O. It's going to go to propene, which is C3H6. So it's a 1-to-1. They tell us the MR of this, they tell us is 60 for that one. And they tell us it's 42 for that one. Okay, so let's work out how many, we start off with 50 grams of propan-2-ol. With 100% yield, what will we get? Okay, so let's do the moles of propanol, mass over MR, mass over MR, so we've got 50 grams over 60. That's 56.83 recurring. Okay. So that means the moles of C3H6 we're going to get should be the same. It's a 1-to-1 ratio, 0.083. Okay. So the mass of C3H6 should be equal to moles multiplied by the MR, which is 0.0833, multiplied by the MR, which is 42. Tells us there. Okay, times by 42. That's 35 grams. Okay, so we should get 35 grams, but we only get 30 grams. So the percentage yield is equal to what we do get, 30 divided by what we expect, 35 multiplied by 100, which is equal to 86%. So that is the answer there. Quite a lot of work for 1 mark. Okay. Sulfur dioxide is produced when some fossil fuels are burnt. Okay, which of the following statements is true? Right, sulfur dioxide can be removed from waste gases by reaction with calcium oxide. It can be, yeah. Okay, so CaO plus SO3 goes to calcium sulfite. That's how you remove it from the flue. It is not insoluble in water. So that's going to be the answer. Just check the other ones. It's not insoluble in water because SO2 dissolves in water to give acid rain. Okay, so that's definitely right. Sulfur dioxide is a basic oxide. It's not. It's acidic. Or most non-metal oxides are acidic, and we know that's acidic because it causes acid rain. And it is not an ionic compound because it's between 2 non-metals, so it's covalent. So A is definitely the right answer there. Got a mechanism here. Which of the following is a correct mechanism for the formation of 2-methyl-butyene from 2-bromo-3-methyl-butane? Okay, so right, this is the reverse of the reaction that we actually had earlier in the paper. Okay, so this is elimination. Right, now in elimination, the hydroxide ion acts as a base. That means it reacts with, it removes an H with H plus. That is acting as a base there. It removes H plus. That pair of electrons goes into to form the pi bond, and then that pair of electrons leaves to get the bromine. That is the correct that's the correct mechanism there. But let's just check it's the right thing, the right product. So we've got to make 2-methyl-but2-ene. That would give us that would actually give us 3-methyl-but1-ene. So that's not right. That's going to put the double bond there, isn't it? So that is not the right answer, but the mechanism is correct. The OH minus is acting as a base here, and the pair of electrons go to form a pi bond, so the mechanism's okay. Is it going to give us the bond in the right place? It's going to give us a double bond there, which is going to be 3-methyl-butene. So that is the right one. Let's just check the others are not right. This one is wrong because it's got an arrow going onto the carbon. That shouldn't go onto the carbon. It should go to form a pi bond. So that one's wrong because of that. And this one is acting as a nucleophile. This is nucleophilic substitution. And that would end up giving you an alcohol, not the alkene. So B is the correct answer there. And I nearly said it was A because I didn't read the question properly. Right, 14. An organic compound contain 40% carbon, 6 hydrogen and oxygen. Which of the following compounds could it be? Right, so they've all got oxygen in them, so we can't just eliminate any. Then they've all got carbon, hydrogen. We're going to have to work out the empirical formula. So we're going to say we've got 40. This is the mass. We've got 40 grams of carbon. We have in 100 grams. In hydrogen, we've got 6.7 grams. Now the difference there is that must be 53.3% oxygen. So that's going to be 53.3 grams. Now we need to work out the moles. How are we going to work out the moles? We'll divide by the MR, the AR, the atomic mass. So that's over 12. That's over 1. That's over 16. That gives us 3.33 moles of that to 6.7 moles of that to 3.33 moles of that. So the formula we can see is 1, 2, 1. So it's CH2O is the empirical formula. Well, let's see which one of those it could be. Ethanol, well, that's not right. That's C2H6. Right, there's way too much oxygen, hydrogens there. Ethanoic acid, well, that's C2H4O2. That's not C2H4O2. That could be it. It could be ethanoic acid. Methanol, let's just check that that is the right one. Methanol is CH3O. That's not, that doesn't work. And methanoic acid is, so that's CH2O2, not O. So it can't be methanoic acid. So B is the right answer there. Okay, this one is about polymers. There's the repeating unit of the polymer. Which of the following molecules would form a polymer containing this repeating unit? Well, it's an addition polymer, probably. Okay, so that means what's happened is that you've got a double bond there, and these weren't there. That was the, so let's number that. What would you call it? It's 1, 2, 3. So it is going to be methyl propene is the name of that molecule. Yeah, you've got 1, 2, 3 carbons and a methyl group on number 3, and a double bond between carbons 1 and 2. Methyl propene is the answer. The others all got 4 carbons and they're all wrong. Okay. All right, maximum Boltzmann curve. Okay, which of the following statements is true? Position A represents the mean energy of a molecule. That's not right. Okay, it's not. That's the most likely energy, but the mean energy is going to be, because the curve's skewed to the right hand side, the mean energy is going to be somewhere about there. Yeah. Okay. Addition of a catalyst moves, that doesn't change EA, of course. Oh right, sorry, it does change EA, not yeah, but it won't move if you add a catalyst, it will make EA lower. So the EA would move to the left, not to the right. So that's not, B is not correct. C, the area under the curve to the right represents the number of molecules with enough energy to react. Yeah, so this, yeah, that does represent, that's right. That's the correct one. Let's just see D. The position of the peak of the curve at a higher temperature is further away from both axes. Well, that's not quite right. It's nearer to the bottom. It would be like that. Okay, so it would be nearer to the energy axis, but further away from the particles, number of particles axis. So C is the right answer there. 17, tetradecane alkane found in crude oil. When tetradecane is heated to a high temperature, one molecule decomposes to form one molecule of hexane. So we've got hexane, C6H14, and 3 other molecules. Now, hexane, how do we know it's that? It's an alkane, and it's CnH2n plus 2. Right, so we can eliminate C straight away because it doesn't make any hexane, but A, B, and D do. Let's see, it says 3 other molecules. Well, A is possible because it's making 1 of that and 2 of that. That's okay. B is wrong because it's only making 2 other molecules, so it can't be that. But it could be D or it could be A. So let's see which one is correct. Now, a minute. Right. Now, D can't be right. I'll tell you why, without trying to balance it, is because in cracking, you always get 1 alkane and all the others are alkenes. So we've got hexane, which is an alkane there, but also we've got ethane, that's an alkane, that's impossible. So I think if you add the numbers up in D, it's not going to balance. So it's not D. But A is right. If you add the numbers up, it does balance because you get 1 alkane, and that's an alkene, butene, and that is ethene, that's an alkene as well. So A is the right answer there. The structure of cyclohexene is shown. Which of the following, which is the following general formula of cyclic alkenes such as that? Okay, so that's going to be C6, and how many H's has it got? It's got 1, 2, plus 2 there makes 4, 2 there 6, 2 there 8, 2 there 10. So if you look at that, that is Cn. Now it's not 2n, it's 2n minus 2, isn't it? So B is the right answer there. Okay, now here's an equilibrium one. So I think what we're going to have to do here is draw one of these tables where we have A plus B going to C and 2D. Let's do the start moles, the used moles, and the equilibrium moles. Right, so the start moles, we've got 10, and we've got 10 of B. And we haven't got any of that or any of that. Now at equilibrium, we've got 4 moles of B left over. So that means we must have used up 6 moles of B. Right, now when we use up 3 moles of B, we're only using 1 of A up. So that means we must have used 2 of A. Yeah. So that means we've got 8 left over. Right, now every time we use 1 mole of A, we're going to make 1 of C, so that means we've got 2 of C at the end. And every time we use up 1 of A, we are going to make 2 of D, so that means we've got 4D. So the total moles at the end is 8 plus 4, that's 12, plus 2 makes 14, plus 4 makes 18 moles. So the answer there is C. Okay, the MR of hydrated copper sulfate is 249.6. Which of the following is the mass required to make that much solution? So let's work out the moles of it. So the moles is equal to conc times volume. The concentration is 0.4. The volume is 50 over 1,000, 0.05, which gives us 0.02. Now we have to work out the mass. The mass is equal to the moles times the MR, which is 0.02 multiplied by 249.6, which is equal to 4.992. So the answer is D. Right, so questions 1 to refer to this equilibrium reaction. Which of the following shows how the equilibrium yield, the equilibrium constant are affected by the changes shown? Okay, right, now the only thing that affects the value of Kc is temperature. So we can probably get rid of a load of them. So we know A is wrong. That will not affect Kc. And B is wrong. That won't affect Kc. So we've only, sorry, D is wrong. It's only B and C we've got to worry about. Adding a catalyst does not change the amount at equilibrium, it's just the speed. So B is wrong for that reason. So without worrying too much about all the other things, C is going to be the right answer there. And let's just check. Increase the temperature, you would get a better yield because this is endothermic. And yeah, so that is the right answer. 22. Bond enthalpy calculation. Okay, so use those values to calculate the unknown one. Okay, right, so we need to write down the equation there. So we've got methane. I'm going to write it down as the bonds. So we've got, there's methane, and we've got water, and that's going to give us carbon monoxide and 3 lots of hydrogen. Right, now whenever we do bond energy calculation, what I like to do is I like to break it all up into the atoms. So we're going to have carbon plus 6 gaseous hydrogen atoms plus 1 oxygen atom, all in the gaseous state. And then we're going to reform the bonds to form the new product. Okay, so the blue arrow, we're breaking bonds, so that's going to have a positive value. The blue arrow, we're breaking 4, in blue, sorry. Blue arrow breaking 4 times 413 for the carbon hydrogen bonds, yeah. And we are breaking 2 of these, so that's 2 times 463. And that gives us a value of 2578 plus. Okay, on the green arrow, well, we're forming 3 lots of this, so 3 times 466, and that's negative 463, sorry. And we're forming 1 mole of carbon monoxide, and I'm going to call that X. So, and they tell us the enthalpy change for that reaction. They told us earlier on in the question it was positive. What was it? It was plus 206. I'll just add up that lot together. 3 times that gives us minus 1308. Right, I'll do that in different color. Do that in red. That's plus 206. So using Hess's law, we say plus 206 is equal to plus 2578 minus 1308 minus X for the carbon monoxide bond. Yep. So rearrange all that, we get X is equal to minus 1064. Now it's given us as kilojoules. Okay, it's given us a minus value because we are forming that bond. So the answer is 1064. The answer is B. Okay. Question 23 is the last question. Right. Which of the following changes would lead to the greatest increase in pressure? Okay, so we've got PV is equal to N, PV is equal to nRT divided by V. Right, so we're going to keep the V the same, so P is proportional to nRT. Well, R is obviously a constant, so P is proportional to NT. Okay, so we're going to remember that there. P is proportional to number of moles times by the absolute temperature. Okay, so right, we have increased the temperature from 20 degrees C to 200. So that has gone from, we have to be careful here, it's not 10 times the temperature. It's easy to think that because it's going from, well, we've got our 273, so that's going from 293 up to 473. So we have increased the temperature there by 473 divided by 293. We've increased temperature by a factor of 1.61, right? And we haven't done anything to the moles, right? B, let's see with B, we have added 1 mole of gas to X. So the moles of N has gone from, it's gone from T up to 3. So that is multiplied by 1.5. So that wouldn't have as big as an effect as the first one, which goes up by 1.6. Right, then it gets more complicated. So we've added N has gone to, right, they've gone from 2 to 2.5. So that has gone up by a factor of 1.25. But then the temperature, well, that's gone from 22, so that's gone from 293 up to 423. So that's going to be increased by a factor of 423 over 293. That's gone up by a factor of times 1.44. Okay. So that's going to be times 1.44. So the total increase is going to be that multiplied by that, which is equal to 1.80. Right, and then the last one, let's see here. So we removed 1.5 moles of gas. So N has gone from, we started off with 2. So it's gone from 2 down to 1.5. So that is that's times 0.75. Okay, so it's a bit smaller, less than 1. And the temperature, well, we've gone from 293 up to 573. So that's multiplied by a factor of 573 over 293. 1.95. So that's going to be times 1.95. So the total is 0.75 times that. So 0.75 times 1.95 gives us 1.46. Right, so we can see the biggest overall factor increase is going to be this one. That goes up by a factor of 1.8. So the answer is C. And that is the end. That's the last question.